Okay. Today we are talking our topic about the violations of classical linear regression assumptions. One of the classical linear regression assumptions is about multicollinearity. Okay. We start from multicollinearity. In the assumptions of classical linear regression, is stated that there is no exact collinearity between independent variables. Okay. We have assumption number X here. Classical linear regression model. No multicollinearity among regressors in the model. Now, our discussion today is about what is the nature of multicollinearity. Is multicollinearity really a problem? What are its practical consequences if there is multicollinearity? And how to detect multicollinearity? And the last one is how to solve the problem of multicollinearity. Okay. Okay, this is actually we have two kinds of multicollinearity. Okay, first is a perfect multicollinearity, another one is an imperfect multicollinearity. Multicollinearity is two types here. A perfect multicollinearity. Another one is imperfect. Okay, if our model is perfect multicollinearity, so we cannot if there is a perfect multicollinearity, this means we cannot. So the parameters because the determinants of x prime x is 0. So we cannot calculate the coefficient of parameters. This is if there is a perfect multicollinearity. Okay, if there is imperfect multicollinearity, depend on how strong the collinearity between the explanatory variables. Okay. Okay, here multicollinearity is due to Ragnar-Fish. Originally, it means that the existence of perfect multicollinearity or exact linear relationship among some of all explanatory variables of the regressions. Okay. Okay, in equation 10.1.1 here, there is no any residual here compared to 10.1.2 because 10.1.2 has this residual. 10.1.1 is a perfect multicollinearity, and then 10.1.2 is imperfect multicollinearity. Okay. Okay, here this is for example, we have data here. x2, x3, and then we have x3 star here. Okay, it is appeared that x3 is equal to 5 times x2. This is perfect multicollinearity. 10 times 5 is 50. 50 plus 2 here. Yeah. Okay, this is almost perfect multicollinearity. This one, 15 times 5, 75. Yeah. So we type 18 times 5 again, 24 times 5, and so on. So here, x3 is equal to 5 times x2. Therefore, there is a perfect multicollinearity between x2 and x3. Okay, in this case, we cannot run the model because the correlation between x2 and x3 is very high here. Now there is no longer perfect multicollinearity if, for example, the value of x3, okay, is not like x3 here, but will become x3 star or something like that, because we add some number here in x3 star. Okay, if x3 is exactly perfect multicollinearity. Okay, in perfect multicollinearity, okay, for example, if suppose we have x2 is equal to alpha 1 plus alpha 2, okay, time x3, for example. So we thought any residual here, or we have here x2 is equal to alpha 2 x2, x3 here, x3. Okay, there is a perfect multicollinearity. This is a perfect multicollinearity. This one also perfect multicollinearity. Okay. Okay, another example for imperfect multicollinearity. For example, here we have x2 is equal to alpha 2 x3 plus residual here. Yeah, we have a residual here. This means here, this one is imperfect multicollinearity. Okay, in the case of imperfect multicollinearity, we can still calculate for the coefficient of the parameters. Right? But in perfect multicollinearity, we cannot calculate the parameters. Okay, we continue this multicollinearity. Okay, this is sample here. We have the degree of multicollinearity. This one very high because x2 and x3, they are almost half of x2 is equal to x3 here. This is a high multicollinearity because some part of x2 is equal to x3. Okay, this is a moderate because less multicollinearity between x2 and x3. And if we have here no collinearity, but it is impossible to have no multicollinearity at all, because usually we have low collinearity. Okay. Okay, this one, okay, this one is a question 10.1.5. We have only one x here. For example, this is the cost functions. Cost functions is determined by the output. Here we have output square and output to the power 3. This means only one variable here. The independent variable is actually output, but we square it to be x square and x3 to and x to the power 3. Okay, this is a cube model. So usually in total cost functions, it is possible to have perfect multicollinearity because another x is calculated from the original x. Okay, if perfect multicollinearity is perfect in sense of equation 10.1.1, the regression coefficient of x variables are indeterminate and the standard error are infinite. If multicollinearity is less than perfect, is stated in equation 10.1.2, the regression coefficient, although determinate, but his possess high standard error, so the coefficient become not significant. Okay. What are the causes of multicollinearity? Okay. There are several sources of multicollinearity. The first one is data collection method employed. For example, the sampling offers a limited range of values taken by regressors in the populations. So I mentioned already, you must have large sample size to avoid the perfect multicollinearity. For example, here, if we ask from the student in this class, okay, if I ask one by one here, okay, your age, this is around 20 to 21 or something like that. This means if you have, if in the class only 14, this means okay, for the first sample, second, third, fifth, sixth, 7, 8, 9, 10. For example, we have 13, for example. You have age here, 20. For example, here, 20. 21. Okay. This means we have almost the same number here. There is no big difference between the sample because the sample size is very small. So in this, in your research, for example, we need large sample size to avoid this perfect multicollinearity. Okay, this is a limited sample size. Okay, this is one source of multicollinearity, the first one. The second one concerns on the model of population being sample. For example, in the regression of electricity consumptions and income and house size, usually income and house size will have a high multicollinearity because household that have high income will have a big size of house. So the correlation between income and house size become perfect multicollinearity. And the third one is model specifications. For example, in our model of total cost functions, this is a polynomial model. If we add some regressors in our model, for example, from x, the same x, and then we make it become square x and cube x, so we have the same value. So there is a possibility they have perfect multicollinearity. And the fourth one is offer determined model. This happens when the model has more explanatory variable than number of observations. For example, okay, here. So why I ask you to have large sample size? Okay, for example, we have this equation, demand, okay, for electricity, for example, this one beta 1 plus beta 2, this is income, plus beta 3, price of electricity, okay, or here is tariff, plus beta 4, we have here family size, beta 5, we have here expectation, beta 6, we have, for example, regional, dummy regional, okay, dummy for regional, okay. For example, for the urban and rural area, and we have beta 6 here, beta 7, I mean, beta 7, for example, okay, we have, okay, for example, we have only 7 parameters in our model. This is residual here. Type E for, okay. For example, you collected the data from, the data are collected from the PS, for example, for the years of 2010 to 2019 for samples. Okay, this means you have sample sizes. Yeah? How to calculate sample size? Okay, this one sample size is, this is calculated by subtracting 2019 minus 2010 with plus 1. This means we have 10 years. Okay. So our degree of freedom here, degree of freedom for our model is n minus k. Yeah, that means we have here n is 10 years minus k. We have k years 7, 6, 6 here. That means we have degree of freedom of 4 here. But if we look at the distributions of Durbin Mason, for example, the minimum size for degree of freedom is 16, but we have only 4 here. So because we have too small sample size, this will create the problem of multicollinearity in our model. So please find long sample size to avoid the perfect multicollinearity. Okay. And additions for the reason for multicollinearity, especially in time series data, might be the regressors included in the model shares a common trend. This common trend is, for example, for common trend, in the, okay, we can see the data. For example, we include the sessional dummy variables. We will know that, for example, the demand for certain goods in the winters will be the same for all winter's time. Okay. Okay, here, for example, the regressions of consumption, expenditure, and income, wealth and populations, and regressors income and wealth and population might all be growing over time at a more or less the same. Okay. For example, if income increase, that means wealth will increase and population also always increase. So there is a possibility the relationship between income and wealth will have high collinearity. Okay. What is the consequences of perfect multicollinearity? If perfect multicollinearity, we cannot calculate the parameters. Okay. Now we are talking about imperfect multicollinearity, because in the presence of perfect multicollinearity, we cannot calculate the residual the parameters. For example, here, because we have 0 here, 0. This means any numbers divided by 0 is undetermined. So we continue in the high but imperfect multicollinearity. Okay, the perfect multicollinearity situations is a pathological extreme. Generally, there is no exact linear relationship among X variable, especially in data involving economic time series. Okay, if we have long time series data, we can avoid the perfect multicollinearity. Thus, turning to the 3 variable model in the diffusions form given in equation 10 to 1 instead of exact perfect multicollinearity, we have here we have in 10.3.1 we have residual here. This residual represents some number here. So between x3 and x2 is not perfect multicollinearity. Okay. Okay. If there is not, there is imperfect multicollinearity, we still can calculate the parameters, but usually the parameters will have high standard error. Okay. This is theoretical consequences of multicollinearity. Recall that if the assumptions of classical model are satisfied, the estimators of the regression estimator are blue. Here blue best linear unbiased estimator. Okay, if the normality assumption is added, okay, but it can be shown that if multicollinearity is very high, as in the case of near multicollinearity, the OLL estimator will retain property of blue. Then, what is the multicollinearity? First of all, Christopher Chen remarked these quotations. Beginning student of methodology occasionally worry that their independent variables are correlated, but here normal in economics, because impossible to avoid if income increase. So the demand for certain goods will increase. If the demand for certain good is increase, then the price of the good will increase. So the relationship between income and price will have multicollinearity. Okay, but multicollinearity violate no regression assumptions. Still unbiased, still consistent. Okay, but the estimator will have high standard error. Okay, the standard error. If the higher standard error, that means we have small t ratio. If we have small t ratio, the variable become not statistically significant, different from 0. Okay, but having small number of observation also has the effect. As thus having independent variable with small variances. Okay, in fact, at theoretical level, multicollinearity, few observations and small variances on independent variables are essentially all the same problems. What should I do about multicollinearity? Is a questions like, what should I do if I don't have many observations? Okay. To drive home the importance of sample size, Goldberger contained the term micronumericity to encounter the exotic polysyllabic name multicollinearity. According to Goldberger, exact multicollinearity, micronumericity, the counterpart of exact multicollinearity multicollinearity arise when n sample size is 0, in which case in any kind of estimation is impossible. Near micronumericity, like near multicollinearity, arise when the number of observations barely exceed the number of parameters to be estimated. So please find large sample size to avoid this problem. Okay. This is practical consequences of multicollinearity. Okay. In the case of near or high multicollinearity, one is likely to encounter the following consequences. Although the coefficient is blue, the OLS estimator have large variances and covariances, making precise estimation difficult because we have large what we call it confidence interval. Okay, because of consequences number one, the confidence interval tend to be much wider, leading to acceptance of zero null hypothesis. For example, here, okay, if we have this model, suppose we have model here, we have demand for rice, for example. Okay, this demand for rice here is functions of beta 2, price of rice here, plus beta 3, is income, plus beta 4, family size, beta 5, here other price of staple food, okay, plus beta 6. For example, we have here expectations, and last one we have residual here. Okay, because of the multicollinearity, so we have the coefficient of B3 is statistically not significant. So we cannot conclude, we cannot make conclusions for this because it is impossible without money. We can buy the rice. So theoretically, income is very important variable in demand functions. But according to our estimated results, we have beta 3 is not significant. So we cannot conclude that the income is not essential in the model because we have multicollinearity, very high multicollinearity. So to avoid these misleading results, it is better to find more data if it's possible. Okay. Otherwise, we can, for example, we make a pool data or panel data model. Because of course, the number one, T ratio of one or more coefficient tend to be statistically insignificant. Although T ratio or one or more coefficient is statistically insignificant, but R square, okay, R square usually very high. Okay, in the presence of multicollinearity, okay, usually R square in the case of multicollinearity is very high. High, but the parameter, one of parameter is LH is not in the case of multicollinearity, usually we have high R square but small T ratio. Okay. Okay, number 5. The OLS estimators and their standard error can be sensitive to small changes in the data. For example, if we add some data to our model, the coefficient of estimator will change, and also the standard error of parameters. Okay. In the presence of large variance and covariance, so we have not significant coefficient of parameters. Okay, how to calculate? Okay, how to calculate the multicollinearity? Here we have variance inflating factor, VIF here, equation 10.5.1. Okay, here's how to calculate the to detect the multicollinearity. We use this variance inflating factor. Okay, here this one R square 2, 3. This is the relationship between variable number 2 and variable number 3 of independent variables. Okay, this is the rule for inflation for multicollinearity. Okay, if we have variance inflation factor more than, for example, here variance inflation factor, if we have the correlation between variable number 2 and variable number 3 is 0, then it means we have variance inflation factor is 1. If we have 50% the correlations, we have 1.33. Okay, usually if we have this one, it's very high. Okay, from more than 5.5, we'll have a high perfect multicollinearity, high multicollinearity. Okay, usually if we have only 0.6, something like that, it is still acceptable for our model. Okay, this one, the correlations between the two variables. Okay, this is the consequence of high multicollinearity, while the confidence interval, insignificant T ratio, okay. High R square, we have high R square, but a very low T ratio. We have sensitive to OLS estimator. If we change the sample size or we add some sample size, this is a hypothetical data. We have very small sample size, only 5 here. Okay, this is this data have possibility high collinearity between this variable. This is a sample. We can calculate it. Table 10.5. Okay, to illustrate various points made thus far, let us consider consumption income example from the introductions. Table 10.5 contains hypothetical data on consumptions, income, and wealth. It assumes that consumption expenditure is linearly related to income and wealth. Then the table 10.5 will obtain the following regressions. Okay, we have this one, these equations. Okay, we can see here the T ratio here. T ratio is very small. Okay, very small. Also, we have high R square here, almost 100% here, 96%. Okay, we have degree of freedom is 7 here. Okay, this is the data. This is hypothetical data. Okay. this confidence interval here. Okay, and we regress the x here. We regress here. This we show that there is almost perfect multicollinearity between x2, x3, and x2. Okay, suppose we drop one variable. Okay, one variable. Here we have only income for the consumption function. We have T ratio, higher T ratio compared to the previous model. Okay, because x3 and x2, there is correlation between x2 and x3, because if income increase, then the well will also increase. This is data for consumption functions of United States from 1947 until 2000. Okay, this is table 10.7. Okay, you can calculate by yourself. I will show you this example. Okay, now we detections of multicollinearity. Multicollinearity is a question of degree, not of kind. Okay, meaningful distinctions is not between the presence and the absence of multicollinearity, but within how high the correlations among the explanatory variables. Okay, since multicollinearity refers to conditions of explanatory variable that are assumed to be non-stochastic, it is a feature of the sample, not the populations. Okay, this is a sample problem, not population problem. Therefore, we do not test for multicollinearity, but can, if we wish, measure its degree in particularly sample. Okay, what is the indication of multicollinearity? Usually we have high R square, but very low T ratio. This is indication of multicollinearity. High pairwise correlations. Pairwise correlation is mean the correlation between x2, for example, with x3, or x3 with x4, and etc. Okay, examination of partial correlation. We can calculate the correlation between x2 and x3, x2 and x4, and x3 and x4, etc. Okay, if we have high collinearity between or among the regressors, this means we have a high multicollinearity. Okay, this is auxiliary regressions. Same multicollinearity arrests because one or more of the regressors are exact or approximately linear combinations of the other regressors. One way of finding out which x is related to other x variables is to regress its x on the remaining x variables. So we can regress x with x. This is we call this auxiliary regression model. Okay. Okay. How to solve the problem of multicollinearity? One, do nothing. This is a very good statement. Okay, very nice statement. Do nothing. Okay, I will explain for you why we do nothing. Okay, for example, if we have, okay, the parameters, method parameter statistically and theoretically significant. So do nothing. Okay, do nothing. Okay, don't worry. Okay, if you have multicollinearity, but you have the parameters are statistically and theoretically significant, do nothing. Okay, don't worry. If other lecturer says you must drop one variable or you have to remedy this one and this one, no need. Just take this book, okay, show them that this Gujarati from page 342, do nothing. Okay, this is the first rule for the presence of multicollinearity. Okay, do nothing. Okay. Number 2. Yeah, this is rule of thumb procedures. Number 2, combine cross-sectional and time series data. That means we have number 2, do nothing. Number 2 is we have full or panel data. We can combine this one. We have full or panel data. Number 3, we combine this to get more sample size. Okay. Number 3 is drop a variable. Okay, drop one of variable. Okay, for example, in our model, drop one of variable. Drop one of variable. Okay, that has high collinearity with the other explanatory variables. Okay. Just drop, for example, we have income in our example and wealth. For example, here, income and wealth usually this one have high collinearity because if the income increase, that means then the wealth also increase. This is normal. Okay, if your income increase and your wealth will increase also. Okay. Number 4. Okay, transform variable. Okay, usually we can transform variable. For example, we can transform become first different. This one is first different. 10, 8, 5 is first different. We make differencing from the data. Okay, t time t minus t minus 1. Okay. That means this period subtracted from previous period. Okay, transform variable, the first different form. Or you can also make this one. For example, we have income here, we have populations, we can make this income per capita. Or we can divide it by inflation factor. So we get a real income variable. Okay. Add some new data. This is a big problem. Okay. For example, if we have secondary data, we calculate, we obtain the data from other institutions. So it is impossible to add the data unless we can transform data from low frequencies to higher frequencies. Okay. Reducing collinearity in polynomial regressions. For example, we have cost functions in our previous model. If we have cube model, we can decrease to be square model. Okay. And number 7, other method for measuring multicollinearity is we have factor analysis. But this model or rich regression is not, I don't encourage you to use this one, it's number 7. Because if we add and we drop one of variable based on theory, okay? Okay. Okay. Do you have any question before I show you how to use this multicollinearity? No? No any questions?
Yeah, I want to ask, like, when we want to like do regression on issues that, like, example, during this COVID-19, you know, the duration for COVID-19 is not long, it's too short from 2019 or 2020 to now. So, like, what the focus area is this 2-3 years. Now, the data that is possible to have within this duration is too short.
You mean the COVID effect?
Yeah, example, yeah, maybe
okay.
on
what the dependent variable?
Like you want to see like the income of people.
Okay.
Or
okay.
It is affected, yeah.
Okay. Okay. For example, for income, we have the proxy data. Proxy data, for example, we can use industrial production index. Okay, industrial production index usually in monthly data. Okay, and this one the proxy for the income. Okay, or you change the topic. Okay, change the topic for example, not for the income but for the listed company performance. For example, we have data from stock exchange, Indonesian stock exchange. We can calculate the effect of COVID-19 on the certain sector. For example, we have industrial sector, bank and financial sector, banking and financial sectors, or in the agriculture sector, mining sector, for example, this one. Okay, I think it is better to use this data, because if we use income, the first problem, okay, income is exogenous variables. You cannot increase your income by adding by yourself. For example, okay, this month I want to write down my income $10,000 US, for example. You cannot do this because income is explanatory variable for everyone. Usually, we use the data about the performance of companies, okay, or economic growth, for example. Is it possible to do this? Okay. Okay. In the case of COVID, for example, you can find another data. Okay. Unless you have primary data. Primary data, you can do your survey by asking people for the certain sectors. For example, freelance workers, freelancers, for example. You can ask what is the income before and after COVID, or during COVID. Is there any difference between before COVID-19 and during COVID-19? Okay, you can use this primary data. Okay. Any other question?
Yeah, yes, sir. I have a question. For instance, if you are running your you want to get your regression result, you want to use the EVs, and in relation to multicollinearity, problems of multicollinearity. Now, for instance, if you have a large sample size, let's say 16 and above, then you still have the problem of multicollinearity. Can you tell me what will be the possible cause and how to solve such a problem?
Okay, I will show you. Okay, I have data here. Don't worry. I will show you. We have data here. Okay, I will show you here. This is big size data. Actually, I will show you later, but because you have these questions, okay. Now I will show you this data. This is real data of Indonesian economy. This is real data. Okay, we have data from 1990 to 2021. First quarter, we have quarterly data. Okay, can you see this?
Yes, sir.
Okay, this is long sample size. We have a sample here, 125 sample size. Okay, let me show you the equation. Okay, for example here, okay, we use FUs here. Okay, this is the case of big sample size. Okay, we can compare it with the small sample size later. Okay, what is the consequences of small sample size? Okay, here I will show you this. Okay, now let me show you. Can you see this one?
Yes, sir.
Yes, sir.
Okay, we have here FUs. Okay, now I finish this data. I input the data. Okay. Okay, now, for example, we run the demand for money M1. This one M1. Okay, we choose M1. Demand for money depend on usually in GDP for income. We have GDP here, and we have interest rate. We have also inflation here. Okay, inflation. We choose here. This is demand for nominal money. Okay, this is a linear regression model. Okay, we get here. Okay, we have GDP is significant theoretically and statistically. Can you see this one? This one positive. Okay, and we have rate. Rate is interest rate. Is not significant. It is usual in money demand. M1 is a narrow money demand. Okay, not broad money demand. This means interest rate is not sensitive. The demand for money is not so sensitive to interest rate, but the sign is still significant because negative. Okay, but it is not significant statistically. Okay. Inflation is positive. This means if price increase, the demand for money also increase. Okay, because the price increase, so we need more money to buy something. So we need the demand for money will also increase. Okay, this one the sample of large sample model. Okay, now we can variant inflation factor here. Okay, yeah. Okay, we have variant inflation factor GDP here, 5 point something, inflation rate something. Okay, and we can also run our data here. We estimate. Okay, this. Okay, let me freeze this one. Okay, now we estimate the variable here. GDP with inflations. Okay, usually it is high correlations. Okay, for example here. Okay, this one very significant. Okay, this positive. If price increase, the income increase, or we estimate this one, the effect of GDP on the price. What is the result? Also significant. That means if income increase, the price also increase. Okay, this very high correlations. Okay, this 1.79 something. Okay, now okay, we run again with the sample from Gujarati here. I will show you this one. This one, the sample from Gujarati, table 10.5. Okay. Now I make some modification here. Okay, sorry. Enable it. And then we delete this. Okay, we save here. Okay. Table 10.5. Okay. Okay, now we use this data. Okay, we have table 10.9, 10.5, sorry. Okay, now I change the data from this one to new one, new data, sample, data, new data. Sorry. Okay, now we have new data here. Okay, can you see this one? Okay, I finish it. Now I run link put this to external. Okay, now we have new one here. This one y x2. Sorry, let me choose again x2 x3, and then we open this equation, new equation model. Okay, here we run this one. Okay. Okay, we have this one. None of the variable is statistically significant here. You see? Very high probability. Okay. This we have two examples here. One from large samples, another one from small sample size. So why always we say for you, please find high, large sample size to avoid the problem of multicollinearity, heteroscedasticity, and other violations of classical linear regressions. Even though we have unbiased estimator, but we have not efficient estimator. Okay, this is why we always say that please increase your sample size. Okay, any other questions? Okay, let me show you again. We can find here variance inflation factor. Yeah. We have, you see here, 4,000 something. Okay, 4,000. Okay, if we run x2 with x3, for example, what is the result? Okay, we have 99%, almost 100%, the correlations between x2 and x3. Okay, you get it?
Yes, sir.
Okay. Any questions? No question now?